Hello everyone, I'm Xupeng from Columbia University. Today I'm presenting design and verification of the ARM confidential compute architecture. This is a joint work between Columbia and ARM. System software like operating systems and cloud hypervisors have the most privileged permission in computers. They have full access to all application data above them. This raises data security concerns, especially in cloud computing. For example, cloud hypervisors have full access to the data of virtual machines. Applications running on the virtual machines may generate sensitive private data like financial and healthcare data. Users have no choice but to trust the cloud hypervisors. However, cloud hypervisors are so complex and are not trustworthy. For example, a widely used hypervisor, KVM, contains 2 million lines of code, and tens of vulnerabilities are discovered every year. Besides, many vulnerabilities have also been discovered on cloud service providers, such as Microsoft and AWS. On top of these commodity hypervisors, the data of millions of users are at risk. To address these challenges, we designed a new confidential compute architecture named CCA. CCA allows users to deploy applications or virtual machines while preventing access by more privileged system software such as hypervisors. All VM management operations from hypervisor should be interposed and validated by the CCA, so users no longer need to trust the hypervisor. However, if the CCA implementation has bugs, all these good properties will be violated. We must formally verify that the CCA implementation is correct, which is quite challenging due to its complexity. First, verifying CCA must consider lots of ARM hardware subtleties, including ARM's relaxed memory behavior, page tables and TLBs, hardware access controls, and so on. Second, to deal with hardware subtleties, many components of CCA are implemented in a mix of C and assembly, and even inline assembly code. Thus, composing the proofs are challenging. Third, for better performance, CCA implementation leveraged lots of fine-grained data structures and logs, and even log-free data structures, which complicate the concurrent reasoning. Finally, CCA relies on the hypervisor to manage VM resources, but does not allow the hypervisor to access VM's private data. How to define and prove the security policy is challenging. Although there are many existing verification frameworks and verified system software, none of them can address all the above challenges. We introduced a new verification framework named the VIA to untangle all these challenges and successfully verify that CCA protects users' private data in all circumstances. Our verified CCA design and implementation will be shipped with the ARM v9 architecture and will be used to protect the data security of millions of users in the future. Let me first introduce CCA. CCA will be included as a firmware called RMM in ARM v9. RMM means Realm Management Monitor, and the protected virtual machines are called realms. The verified source code of RMM is provided by ARM. It cannot be modified by any third-party developers, so Realm users don't need to trust any service providers. RMM is designed to be minimal and compatible with the existing software stacks. To be minimal, RMM does not implement any allocation or scheduling algorithms, but exposes resource management interfaces to the hypervisor. Hypervisor must manage realms through RMM's interfaces, including creating realms, allocating memory to realms, and scheduling realms to run. RMM will validate the calls invoked by the hypervisor and will reject if the hypervisor is going to compromise realms' data security. To be compatible with existing system software, RMM exposes fully dynamic interfaces to the hypervisors, So the hypervisor can still control everything and reuse the existing algorithms to manage realms. For example, memory access is controlled by a new labeling system backed by the ARM v9 hardware. Physical memory pages can be labeled as real memory and non-secure memory, and ARM v9 guarantees the untrusted hypervisor can only access non-secure memory. The labels are dynamically managed by the hypervisor through RMM's interfaces. Initially, all memories are non-secure and belongs to the hypervisor. Before allocating memory to realms, hypervisor should delegate non-secure memory to real memory so that it no longer have access to the real memory. Then hypervisor can map the delegated memory to the realm through another RMM interface. RMM will then map the page to the nested page table of the realm. The nested page table is used to guarantee memory isolation for different realms. However, for example, if the hypervisor maps a non-secure page to a realm so that the hypervisor can access the page later, RMM will reject this command. Although RMM is designed to be minimal, it still involves thousands of lines of code to support all realm management services. A single bug in RMM may compromise the security properties of the entire system. To guarantee RMM implementation contains no bugs, we must address all previously mentioned verification challenges and fully verify RMM's correctness and security guarantees. Then we'll talk about how to verify RMM using our new verification framework, VIA. We built a new verification framework, VIA, in which we introduce new techniques to overcome all the verification challenges. VIA introduces a mover oracle query to handle fine-grained concurrent data structures and logs. It also introduces a set of permutation conditions to simplify the proofs of relaxed memory behavior. To support a mix of C and assembly code, VIA introduces register counting. Finally, VIA introduces an ideal concrete machine model to define and prove RMM security. Due to time limit, we'll only discuss the mover oracle queries and the security proofs. VIA introduces mover oracle queries to enable the CPU local reasoning for fine-grained data structures and logs. We'll illustrate how it works using a real example in RMM. Recall that RMM maintains a nested page table for each realm. It may update the same page table from different CPUs simultaneously, which requires synchronization. Instead of using a single log to synchronize the whole page table, RMM uses hand-over-hand log to increase concurrency, so that multiple CPUs can access the different branches of the same page table simultaneously. Here is an example of how hand-over-hand logging works. If we want to update node D in the page table, we should first acquire A, the log of the root A, then the log operations are recorded as an event in the bottom. To jump to B, we acquire log B and release A, and then we jump to D. And finally, with holding the log, we can update D and release D. Actually, in a concurrent system, other CPUs can interleave with the local CPU and also generate events. For example, after we release the node A, other CPUs can start walking the tree as long as they go to different branches. They can acquire A and acquire G, and then release A similar to the local CPU. And actually, other CPUs may generate events after every local steps. Similar to the previous work, Certicals and SEKVM, we use oracles to encapsulate other CPUs' events, denoted as the gray circles. Using oracle, we can focus on the current CPU's behavior, and all its interaction with other CPUs can be simulated by querying the oracles. This is also called CPU local reasoning. However, there will be too many oracle queries for fine-grained concurrency in RMM, making the verification hard and costly. So we introduce mover oracle queries to move, merge, and reduce queries. Mover oracle queries can be moved across local events as long as the machine's behavior is not changed by the moves. Consecutive mover oracle queries can be merged to one. For example, a mover oracle query on the right of an acquire event can be moved across. This is because if other CPUs can do something after we hold the lock, they can do the same thing before hold the lock. Events like acquiring locks are called right mover events. Similarly, mover oracle queries on the left of a release event can also be moved across. Events like releasing locks are called left movers. So the verification task is to identify the mover types of the local events and move the oracle queries as below. We can move the oracle query across acquire A, then acquire B, and acquire D, and release D. Then we can merge the consecutive oracle queries. We notice that the first three events should be equivalent to acquire B with the constraint lock A is free. We can merge the first three events into a single event because there's no interleaving in between. We can show that this event is a right mover if other CPUs will not generate dangling acquire A event. This can be proved as follows. By the previous oracle moves, query moves, there will be no interleaving between any acquire A events and the following release A events, such that other CPU events returned by the oracle queries will not contain dangling acquire A events. Thus, the new event is a right mover, so we can move the following queries. And we do the similar trick again, merge events, identify the mover types, and move the query. Then merge the move query. And eventually, we can prove the page table operation with hand-over-hand lock can be treated as an atomic operation. So the hand-over-hand lock's implementation is proved to be correct. Then we'll talk about how to verify RMM security policies. The challenge is how to specify the security policies of RMM to make the proof easy. Most of the previous verified systems, like SEL4, Komodo, Certicos, and SEKVM, uses indistinguishability to specify and verify its security policies. Indistinguishability is a technique to discover information flow. In the example, we use white blocks to represent A's data and use gray blocks to represent B's data. Let's consider the following two executions of A. A writes 2 in the first execution, but does nothing in the second execution. If B cannot read different values and distinguish these two executions, there is no information flow from A's write to B. However, for example, if A's write also modifies B's data, B will distinguish these two executions by the read. It means that there is information flow from A's write to B. Previous verified systems use this approach to discover data leakage. However, it is infeasible to specify RMM security policy using indistinguishability. First, since RMM relies on the hypervisor to manage all resources of realms, there will be a long list of legal information flow from the hypervisor to the realm. For example, hypervisor is allowed to unmap pages from realm. In this diagram, hypervisor unmaps realm's page in the first execution, but does nothing in the second execution. And then the realm can distinguish these two executions, since the first gives a page fault and the second is a normal read. So there generates an information flow which is legal. It is hard to figure out the long list of legal information flow from RMM and prove that this list is complete. Second, indistinguishability is hard to prove for concurrency. For example, in execution 1, the realm is only scheduled to run +1 once, while in execution 2, the realm is scheduled to run twice. Therefore, in execution 1, the realm obtains 1, while in execution 2, the realm obtains 2. Such difference is due to scheduling rather than information flow. Thus, we introduce an ideal concrete machine model to address the difficulties. The ideal model forbids the hypervisor from accessing realm's private data by definition, while the concrete machine is just RMM specification. By proving the concrete machine refines the ideal machine, we can show that RMM satisfies the security policy defined by the ideal machine. In our approach, the ideal machine forbids illegal behavior rather than enumerating all legal information flows. Also, the ideal machine uses the same mover oracle as the concrete machine to handle concurrency. This guarantees that they generate the same interleaving and other CPU's behavior are the same. The concrete machine is the RMM specification. It is a physical memory with different labels. All realms, RMM, and the hypervisor will access the shared physical memory. In the ideal machine, each realm stores its private data in a logically isolated memory. There are realm memory 1 and realm memory 2 in the figure. Only realms themselves can access their own realm memory. RMM and untrusted hypervisor should work the same as before and can only access the physical memory. Note that the physical memory still contains a region labeled as realm, but that region is empty in ideal machine. What we need to prove is that the two machines always have the same behavior. For example, if the hypervisor unmaps a page from a realm which is legal, both machines will keep the same behavior. Because the nested page table of realms are not in logical memory, so they are the same in the two machines, and the realm will get the page fault in both cases. Therefore, no security issue was detected. However, if the hypervisor can illegally change realm's private data, in the concrete machine, realm will read the poisoned data, but the ideal machine, realm, will still read the original data from the logical memory. This caused different behavior of the two machines, and we can detect a bug. Then we discuss evaluation. RMM developed by ARM and verified by our Columbia lab in parallel. We've gone through 3 iterations of development verification cycles. It turns out that after extensive testing, our verification procedure still found 8 vulnerabilities in RMM. The verification took 2 person-years in total and finished just a few months after the development of the RMM prototype. Another good news is that the verified RMM does not bring a significant performance overhead compared with the original prototype, shown by our performance evaluation. To summarize, we introduced the CCA to protect users' private data. We introduced the verification framework VIA to verify the correctness of CCA. Our verified CCA design and implementation will be shipped in our ARM v9. Thank you.